Okay, I'm gonna get started. So the goal today is to cover choice models. If things go as planned, roughly by the end of today's class, you should have sort of all the technical tools you need to at least understand the human preference learning parts of most modern, or at least many modern sort of learning from human preference pipelines. So this would be a lot of the fundamentals, but as you'll see, many of the models and approaches people use end up reusing many of these ideas. So think about these as one of the sort of foundational methods lectures. So the goal today, as mentioned, we're going to talk a bit about standard quote unquote rational choice models, and we'll focus on the discrete setting. So choice modeling has a long history. I'll give some historical context in a little bit. But one way of thinking about the goal of choice modeling are a set of tools that help one predict choice behavior of either individuals or a group, generally within a specific context. So if you like, like many things that we like to do within sort of machine learning AI models, the idea in choice models is that I get to observe either an individual or a bunch of people making choices. This becomes my data set. And the choice model is literally what model can I fit to this data set such that given a new context, I can predict the choice that people might make. And so as we go through, I'd like to encourage people to also engage meaningfully with the assumptions that we're making. I'll try to call them out as we go along. Those assumptions are important, and part of this class would be sort of critiquing some of the assumptions that we make when we try to build choice models. Okay, so, applications all over the place. Here's a simple one. I'm interested in modeling, say for marketing applications, what preference or what choice people might make. Suppose I'm either, say, a car dealership or I'm running a website that compares cars and sort of sells people cars. I may want to be able to sort of predict something about preferences that people that come to my website or people that look at cars might want. And so, like everything we do in learning, the things you need generally are sort of some set of features that describe sort of objects. So for instance, for cars, you might have the brand of the car, you might have the price, invoices, a bunch of other information. You can encode this in a bunch of different ways. And then you might want to know something about the decision makers. It's not here, but individuals, something about maybe either expressed preferences, maybe demographics, often might be predictive signals. If you have other signals about things about, I don't know, background, previous cars that they have driven, these might be some good features to extract in trying to predict when they come to your interface, what they might choose as the preferred car or how they might rank different options across these sets of items. You can also do this for transportation. So this is actually a quite popular real-world application. So you may ask questions, for instance, I want to do route planning. So I want to make choices about, say, between some set of routes. There are ways to do this in break up the route into multiple steps, and you're making choices around sort of specific paths to take. Or you can think about this as a sort of global choice modeling. So I have a discrete set of possible paths, and I want to understand and model and predict for a particular individual what their preference might be in terms of the routes. So things like this are often used in route planning algorithms that are part of, say, many of the sort of mapping algorithms. They're even more so used in things like logistics planning. I alluded to this last time, but say delivery and sort of other aspects of logistics applications. You might take into account things like weather. You might take into account traffic. For the user, you might take into account whether they like to drive as fast as possible but are willing to take a longer route, or they would prefer actual literal shortest path, even if it means that they're driving slower, things like that. You might also include cost in this. So you can do this, again, through features, or you can do this through sort of other kinds of elicitation mechanisms. We'll go through some details on applications in a little bit. But you might want some signal on, say, how much the particular user is willing to pay. You can think about this for, say, fuel. You can think about this for tolls, a bunch of other choices. That will be part of your choice model. Okay, other applications, things like energy. I think this fits well within sort of planning, logistics, things as well. So lots of fun applications. There are papers here if anyone's interested in applications. In a bunch of other contexts, I'll have you take a look at it. Another fun one, but maybe one that's sort of sufficiently simplified so we can engage with it. You want to plan the activity sequence for an individual and sort of make choices about, say, ordering of activities, particularly depending on sort of what things are adjustable and whether they might, say, drive or walk. And so you might want some model of what they might do over the course of the day. And so, some activities are fixed. Some activities may have some ability to adjust things. Again, you might want to model individual actor behavior and then use this for signal to model preferences. We've already talked about this quite a bit. So this was the discussion that we spent the most time on over the last couple of lectures. So language, we again use similar kinds of tools, similar kinds of ideas. To model, here we're modeling choices of some decision makers, typically in this second stage. But you might go in the second stage and try to model choices of decision makers across preferences across documents. And so we'll talk through sort of what kinds of models one might use for these kinds of discrete choice problems. All right, so a bit of history to set the context. So choice modeling has a long history. Some of the earliest recorded history is work by Thurston looking at food preferences in the 1920s. Some of this work evolved eventually into applications in macroeconomics, utility theory in the 70s. And in fact, some of the work done at this time eventually led to the Nobel Prize in 2000 to McFadden on the theoretical basis for discrete choice. Again, some of what we'll talk about a little bit today. There's work in psychology. Some of these models actually that they built quite a while ago end up still being quite useful and, again, are some of the key tools that we use now. So, for instance, work by Luce on logic analysis for qualitative choice behavior in 1959. I've already talked about sort of marketing applications, so maybe not surprising. Thinking about predicting demand for new products and then trying to do this within, say, constrained cost settings. So when your different products might be asymmetrically expensive to produce, and so you want to get a sense of demand so that you can maybe do some planning in terms of what you might actually produce. Okay. We talked a bit about application as well. So in particular, and maybe interesting for folks here, some of the original route planning and sort of transportation planning for things like the BART was work done by McFadden to sort of figure out likely preferences across populations as a way to sort of predict how you might plan paths and where you might put stations and things like that. So again, these things have been out for a while. Found lots of meaningful use and some quite important, often quite interesting real-world applications. Okay, so a bunch of references here or allusions to references, easy to look up. Feel free to take a look. Okay, so choice models end up being, as mentioned at the beginning, some of the, at least the quantification and sort of mathematical formalism of choice models have ended up being some of the most useful tools in machine learning when trying to model choice or use choice models, again, within learning contexts. Again, as mentioned, the standard setup is that you ask humans, individuals, or groups about choices across alternatives. you combine this with some featureization, as we often do when we're building machine learning models. So you get signals about the item, signals about the individual, and then you try to build predictive models on top of this. Lots of the core technology for choice models, as mentioned, are, were initially defined in 50s, 40s, 60s, are still the same models we use today. This may not be surprising. A lot of sort of mathematical concepts from a long time ago are sort of still the key technology of what we do today. And so we'll talk through things like Bradley-Terry and Plackett-Luce as some of the standard choice models that were developed a while ago and are useful now for modeling discrete choice. As mentioned a couple of times, I'd like that we engage in assumptions when we're going through these models. So either questions, feedback, I may ask to the class questions, but questions, for instance, about rationality might come up. Most of the models we cover will be focused on discrete or finite choices because they're the kinds of problems that we end up working on the most. But I will give some sort of allusions to other kinds of choice models for those that might be interested. In machine learning problems, again, often there's a ton of context. The context may also be, in many of the classic settings, the context is featureized. So there's a set of features for the item, set of features for the user. And we think of these choice models as sort of learning models using those features to make predictions. In many machine learning applications, there's not an explicit featureization. So again, not surprising to you perhaps, but you might, for instance, use a sentence as the context or like a whole completion of a phrase. And sort of build models that can go straight from phrase completions to a prediction of choice, as opposed to how you might have built choice models in the past, where you'd have an explicit featureization step before you make the prediction. Okay, any questions so far? Again, very high level. If you haven't seen this, maybe context free, but hoping to set the stage. Okay, so discrete choice models. They end up being useful for capturing, or at least they're designed to capture decision processes for individuals, or sometimes can be used for groups. They make the assumption that there exists some utility. You can think about this as benefit. You can think about this as value. You can think about this as reward, because in many of the applications, say in reinforcement learning, what is called reward is equivalent to what economists might call utility. And so the key assumption in many of the choice models is that the utility that an individual gets from, say, a pair of items, say model item A versus item B, is a function of the frequency that they choose item A instead of item B, if given the chance to choose between those items repeatedly. So hopefully it's starting to clarify how you might think about a model for this. Again, the data is some individual described in some way. They get to see a pair of items. You get to measure their choices, whether they choose one item over the other over multiple runs. And this becomes sort of the data on which you build a model that predicts in future what choices they might make. In general, and in a lot of this space, the true utility is assumed unobservable. So there's an assumption that there exists a utility, like there's some function that actually fully describes the choices the individuals are making, but you don't get to see it. And a claim or the hope is that you can measure this via preferences that are actually sort of stated or revealed over choices. Okay. So how might you do this in math? So additional assumption. So at least for these kinds of choice models, a simple way of modeling this is, again, using this utility idea. So utility, again, this latent variable that captures some underlying true preference. So for an individual n, or sample n, given item I or an item j, the thing that you get to observe is what people choose, right? So I get to see, if I give a comparison I versus j, did they choose I or j? And so the label here is 1 if they choose I over J, 0 if they don't, right? So those are the two options in a pairwise preference setting. But you could also do this for lots of different choices beyond 2. So you could also similarly model an observation of choosing 1 out of K options, and the same exact modeling setup would work. So you get to see these sort of discrete observations of what did a person pick across a set of different options. And then the key modeling setup here. So observation, yes, no, across choices. What did they pick? Modeling, we assume that these choices are generated by an underlying utility function. There exists a utility function such that it describes fully the choice that people are making, stochastically, that people are making. And so a bit more formalism. You might have features. So here I'm having features described generically as Z. These are variables that describe the individual attributes. They might describe also alternative choices. So you can have a large featureization that describes both individual, the option that they're picking, and instead of all other options. A bunch of ways of doing this. We'll talk through some examples. And then you have, from these features, you have some function that maps from the features to the utility, right? So in standard machine, I chose Z, but if you want to map this to standard notation, you could use X just to make sure no one's confused, right? So X is the featureization of individual and choices, some description of those choices. Y is the label. Did they pick A over B? And then I have some function mapping that goes from the inputs to the choice. And the function mapping is assumed to be described by this utility function. Okay. And generally, we pick some function class that we think is sort of a reasonable descriptor of features to choices or utilities that people are driving people's decisions. So a simple example might be, say, a linear model, right? Yes?
So the Z vectors, since it captures just the individual attributes, does it need a subscript I? Or could it just be Z of n?
Yeah, so the question is, does your Z vector need to capture attributes of item I, or sort of how rich, essentially, does he have to be? In most applications, particularly for classic choice models, Z can be fairly rich, so it can, often it's the individual, so there's maybe a need for additional subscript. If you're using this for multiple individuals, that'll be, I don't know, N for the, okay, you can imagine using N for the sample, I for item I, item J, and then maybe K for individual or something like that. Often the Z variables in sort of classic settings will be some large featureization of generally the individual attributes, the item, and also alternative choices, because you might also often I'll give an example in a bit, but your choice may be driven not only by the item that you like, but what else you're comparing it to. And so to capture that intuition, you might have the alternative, sort of other choices, alternatives as part of the featureization Z. And what you want your model to capture, so hopefully what beta when you fit your model captures is how all these features interact to define the utility and the probability of picking item I over item J.
Also, N represents the individual.
Here we're using N as the sample, but nothing breaks if you make N individual. Let's make it individual. Be consistent. That's fine. Yes.
So why Ni is 1 if the nth person picks I item over everything else? But then there can be cases where why Ni is 0 for all I. Like if there is no strict preference for one item.
Yeah. So the question is, what happens? It would actually be interesting to talk through. So what happens if there is no choice, and how can I build in a model if sort of an individual doesn't pick any item over the alternatives? I think that's what you're saying. Yeah. This basic model assumes that you have picked between the alternatives. if you wanted to break it, yeah, it'd be awkward to not have a choice across the key items for at least this class of models. I don't have a good intuition. Yes.
We're going to say the same thing, maybe.
Okay.
One option is just to abstain and treat that as a U.
Sure, you can have a choice that's abstain. And is that what you're saying? Sure, that's an option. I'm avoiding that extension for now, but actually maybe that's a, sure, yes. Okay, so a good way to handle this is an abstain option. And so you're modeling also the choice to abstain. Sure. Other questions I think came up from that. Nope. Cool, thanks for the signal there. Okay, any questions on the overall setup? Maybe a quick sort of, if I gave you data that looked like this and I fixed the function, how might you actually fit a model? Well, what does fit in a model mean? And then how might you fit a model on this data? It's an intentionally naive question, but I just want to make sure we're on the same page. We'll do the awkward pause thing. Wow. It's the obvious thing. Okay, so what do we need to estimate, I guess, given a bunch of data samples? Data samples here being choices of Z, or observations of Z and Y. So that becomes your data set?
Yes, we like want to output maybe a distribution of like the probability of Y being 1 for a particular choice I. Mm-hmm. So we need to do this ton of ways. So like some like parameterized thing, maybe like linear model.
Yeah. So yeah.
Indeed. Go from Z to Y.
Yeah. So if you choose a simple linear model like this, then the thing you need to fit, the thing that your machine learning process will do, is find a setting for beta, which will give you a model such that given a new individual, I now have a way to predict their choice, right? Because if I now give you, if I know beta, then given a new item for an individual, that new item for an individual fixes Z, right? So that fixes this part of the model. From that, I can immediately compute H, at least the expected value of H. I may or may not have a noise model, or this won't capture the noise, but will capture sort of expected value of H. H is exactly the utility function, and I can predict the choice that they would make up to noise by just plugging in whether the H function for item I is bigger than the H function for item J. Right. That's the prediction problem I want to solve. The estimation problem is finding a setting for beta. So this is for a linear model. If I make this a neural network, then this whole thing is a neural network model. I just need to fit that neural network model. Okay, so we'll go in some more detail on what this looks like. Okay, so some implications of the choice model worth going through. So again, remember that the choice model assumes a utility. It turns out that you don't actually estimate the utility, or at least it's the information you get turns out insufficient to actually fully estimate the utility. So while this is written as once I know Z and some function class H, I have an explicit utility function. It turns out that I can't tell in this model if I shift maybe the obvious easy thing is if I add some arbitrary value, so I add some positive constants to all the H's, the choice model remains exactly the same, right? Because both left and right-hand side increase, the ordering information will increase. Nothing has changed in the actual prediction of choices. Also, lots of sort of monotonic transformations of various kinds end up keeping the order. And so all this is capturing and keeping, in terms of the information you're actually getting, is this ordering information across alternatives. But it doesn't actually tell you a precise value for what U is. This is a known issue with these kinds of models. This will come up later in sort of some of the difficulty in getting these things to work. So in a bit more math, the thing that we're trying to capture is the probability of making a certain choice, picking alternative I over all the other alternatives that you could pick. Again, the key quantity in sort of measuring our choice is the probability that your utility for item I is greater than utility for all other items. So this term UNI is bigger than UNJ for all the other items. And as mentioned, I can apply some transformations. In particular, I can rewrite this by just moving this to the left-hand side. I can think about this as the probability of the difference being greater than 0. So scale-free invariant monotonic transformations, good to convince yourself. The additive one is trivial, hopefully easy to see. I'm subtracting the 2, so if I add a positive number, the positive number disappears in this subtraction. But it's probably useful to also convince yourself by scale, for instance, by an arbitrary value, the scaling will go away, or all scalings will have equivalent choices, equivalent probabilities. So any global scaling or any global shift. You can also show that similar things will be true for sort of monotonic transformations of various kinds. So this causes issues. If I fix the context where you expect sort of all the alternatives are comparable, then things are fine. But often we want to sort of take a utility model trained on sort of some model, some context, another utility model trained in different data set, different context, and somehow compare them. Because the H that we learn, the U output, is only good up to monotonic transformations, it turns out that you sort of generally can't compare across contexts in a sort of meaningful way. In the literature, I don't see this that much in the machine learning literature, but if you look at economics and other areas, psychology that uses choice models, often there is a assumption of a normalization that allows for comparability. Now, critiquable about whether this is sufficient or not, or if you need more information to nail things down. But as instead of standard practice, you might, for instance, assume the scale and standardized variance as a way to get a utility function that is on the same scale and thus comparable across different contexts. Okay. So one example of this is when I just have two options. So hopefully we get to the point where, again, this feels familiar because some of the setup might seem a bit unusual. So I have two options. My options are, do I pick the item or not? So I can just ignore sort of the J index for alternatives. And so I have characteristics for individual and item potentially, and the utility function is the same, say, linear model that I did before. If I combine it with the mapping from utility to choice, so just like before, it's just a single utility number. Is it greater than 0 or less than 0? And if it's greater than 0, I'm modeling the choice of picking the item or not picking the item. Easy to show and good exercise for yourself that if the noise model is logistic, what I get out as the probability of picking, making a choice of the item is going to be sort of a familiar, hopefully, logistic function that you might see in logistic regression. And in fact, if I get a data set of choices over alternatives, and I want to fit this model, the actual algorithm I would use is literally logistic regression, right? So I'd have a bunch of features, say we use SN for the features here, a bunch of features for every choice, a bunch of observations of did I choose or not choose the item across a sort of data set. So now I have labels that are binary, yes, no. I have inputs that are some vector, set of vectors, SN, and I would literally fit logistic regression model. And this would give me my parameters beta, right? And this will allow me then for a new individual with the same set of items, I can now plug in the S for the individual, push it through the beta, and then sort of make a prediction on whether they would choose the item or not. So as mentioned in the last class, hopefully logistic regression is familiar. Again, sort of ML 101. So you would just sort of run the same machinery that you would always run for fitting logistic regression. But now the data that you're fitting on are these sort of choices over, or binary choice. Okay. You could do also lots of fun, fancy things. So an obvious, maybe interesting one that you might have seen is choose a different noise model. So suppose you then pick the sort of standard normal instead of logistic, then you get where you can show that then you get sort of a probit type of binary choice model as opposed to logistic model. Okay, any questions on this?
I just had a question earlier about like what happens if someone has no preference. I don't understand how like this would account for that, because it seems like if someone had no preference, like when you learn your beta parameter, that still results in like some inferred preference.
Yeah, so using so one you can't do, or it wouldn't fit well in the binary setting, so you'd probably need at least 3 options, like choose, don't choose, no preference, I guess. If you wanted to use the, what we discussed as an alternative setup for this problem was I create a new choice, quote unquote choice, which is no choice, and just add that into my, and I'll have a triplet of possible options. If you do it that way, then, you can't use this model. We'll do something slightly different. We'll show in a second. It fits into the general context. You just have to modify for 3 options. Your question was also, I guess you're implicitly modeling a choice of no choice. Yes, that's the sort of trade-off of using that kind of setup for this model.
How do we think about 2 samples or 2 individuals having different choice? Would that lead to different learning for different individuals?
Yeah. So the question is, how do I handle multiple individuals and sort of potentially making different choices? So a few different options. One, again, like everything else in machine learning, you make an explicit modeling assumption. And modeling assumption matters and will have an impact on the quality of your results. And you will make all these assumptions in all the ways that we typically make assumptions. Things like, how many samples do I have? So like, am I likely to overfit? So because of this, I make a more restrictive assumption or less restrictive assumption, things like that. We'll talk about this briefly in a second. So for something like multiple individuals, one modeling option is to assume that they all have the same underlying utility function. So they all make choices the same way. So I just think about them as multiple observations of the same underlying utility model. Another option is that they have different U's. And so at least in this model, I don't get any benefit from modeling them jointly. So I might as well just have a separate choice model for every one of them. I could make some other, like another modeling assumption might be they have different betas, but the betas are tied together. So maybe they're additive to each other, or across a set of individuals, the set of betas is low rank, for instance, is another sort of implicit choice you can make. So sort of all of the degrees of freedom that you'd normally have. I don't know if it's a satisfying answer, but sort of the explicit answer is, the decision you make on modeling depends on what assumptions you think are reasonable to make, trade it off with sort of practical estimability things that we typically, but the pragmatic choices we typically make to actually fit machine learning models.
I'm a bit confused. Could you connect this slide with the last slide, like the connection?
Sure. So the last slide was talking about, actually, I think we'll literally do this. Oh, we did not. Okay. So 2 slides ago, I think hopefully the series is clarifying. So here we're talking about discrete choice over an arbitrary set of, the key assumptions here is there's some collectively exhaustive, mutually exclusive, and finite sets of options. Right? And so across all these options, the key assumption I'm making is that the choice that an individual makes in a certain context across items is governed by some underlying utility function, which is some stochastic function that has a deterministic component and then some noise component. And my goal in learning is to estimate the deterministic component so I can make sort of expected choices across samples. So this is the most general, if you like, this is the most general framing we're going to give of this problem. There are other ways to generalize further, but for this class, it's sort of as general as we're going to go. And then the further restriction that we made just now is instead of having some K set of choices that you're picking within, what if I just restrict you to yes or no, picking an item? So now I have only two options, right? And so J is 1 or 2 or 0 or 1, depending on the indexing that you like. It turns out that you don't need to keep J explicit because, okay, actually I may see also the gap that was, okay. So it turns out that you can model this difference explicitly. So I may have UN1, UN2, right, for the two options, binary option choice. As we show here, the actual values don't matter, only the difference matters. If I only have two options, it's equivalent just to have a single U and then like a constant or 0. Right? So once I have that, is that clear so far? So the statement made, again, is general model for utility assumptions across a set of finite choices. I'm going to restrict myself to two options. And I have two options, same exact model, but I have UN1, UN2. Right? And the claim being made here, but useful to check for yourself offline, is that this model with y and 1 equals to 1, 0 if u and 1 is greater than u and 2, and then otherwise, is equivalence in utility model world. There's no difference from the model yn1 is equal to 1 if, say, let's call this u tilde n is greater than 0 and 0 otherwise. Where u tilde, I don't know if you can see, okay, you can still see it. U tilde n is equal to what we were calling un1 minus un2. Okay. And the reason that we can do this is that we know that utility functions, or this whole setup, is scale invariant, monotonic invariant, and all that matters in sort of, the models are essentially like the differences across the utilities. And so it's sort of equivalent to just collapse things out. And so we can collapse them out. And if you do, then you end up with this model, which is exactly the thing on the board, which is the binary version of the general case. Okay. Is that clear? Thank you. Good question. Any other questions on this? Okay. So again, hopefully it's even more clear. Literally I would run logistic regression on a data set that looks like this. This would give me a choice of like a setting of beta, and I would use the beta to make predictions of choices in the future. Okay, so let's complicate things a little bit more. So we can have a slightly more interesting model. Now, again, I keep the two choices, but I'm going to allow the utility to say depend explicitly on, well, just like before, features of item 1 versus item 2. So actually very similar to this model. We'll end up in a similar place. And so, I can make different choices for the noise terms. One choice that's convenient is ID extreme value for the different noise terms for item 1 and item 2. If I do that and I do a bit of sort of massaging on the math, the massaging here is I'm going from, just to be clear on this, I'm going from this statement, which is utility is given by this, and this is the option, yes or no. And I want to understand what is the probability of y equals 1, which is exactly equal to the probability of un greater than 0. Right? So I'm just actually literally working that out. And to do that, I'm going to plug in this function into the un and sort of see what the algebra works out to. So if I do that in this setting, I can write the solution a couple of different ways. One way is to keep the utility separate. So I have probability of choosing item 1 is sort of e to the beta for item 1 plus normalizing constant to make sure they sum to 1. Just like I showed here, you can do the exact same trick. You can do this, different ways of doing this. But if I have a shared beta, so I assume the parameters are the same, then it's exactly equivalent to normalizing out the numerator term so that you get 1 over 1 plus beta Zn1 minus Zn2. So where might you have seen this? The most likely place you've seen this is if you've worked through the math of doing multi-class logistic regression, and you sort of work through what it looks like. So you can either do it in multi-class, but I allow sort of some default class, and you can show that all the weights will look like differences. Or you can look at multi-class logistic regression and ask, what happens if I reduce it to just binary options across choosing between two options? Exact same math. So if you have done that, this may be familiar. If you haven't, useful exercise. And we may test stuff like this, actually, to make sure sort of easy. It should be straightforward, sort of. If it's not, we should work through its manipulations of algebra, yes.
In real life, is it like a valid realistic assumption that the noise is like IID distributed? Or?
Yeah, so excellent question. So, is the noise being independent a realistic assumption? So what this means in this context is that any randomness in the choice of item 1 is independent of the randomness in the choice of item 2. In real settings, maybe there's actually some correlation between the two. The math gets a bit more complicated, but with modern tools, it's actually not that much more difficult to do it. We'll mention some approaches that you might, for instance, you could do some. The obvious thing to do would be maybe a hierarchical model with like parameters for the noise epsilon1, epsilon2, and then say maybe something hierarchical that captures the correlation and try to estimate that. I think that's a very reasonable modeling assumption. In practice, and what you see in most applications is this ID assumption. But just like we make ID assumptions everywhere, pragmatically, and sort of things sort of work well enough. It's probably not reality, but also the sort of other things broken that are not reality here. So I'm intentionally anchoring on, and I like the question because, again, I want to make clear that, as designers in the system, you're making choices about models. And like always, the closer your sort of modeling choices are to reality, the sort of more accurate the models will be. But there's also generally trade-offs with things like sample size, and so pragmatic choices that actually allow you to fit things. So are we getting ground truth? Probably not, but often this is a reasonable approximation.
So I'm just trying to figure all this out. So when we started it, if you can go back. Before this also. So here it's like someone has a choice between let's say 5 cars, and we're trying to figure out for a particular car, we're trying to figure out something because it's you're matching I with all the other J's. And then in the next slide, if you go here, we then move to a scenario where the only option the person has is whether he has to choose this car or not, and there's no other cars.
You could use it for either the choose or not choose. You can also do the same exact model for choose A or B. There are only 2 options. So the math for those 2 settings are exactly the same. The reason that they're exactly the same is this. Right? So I can plug in choice car 1, car 2. Nothing changes in the actual utility that I learned if I just use a plug-in estimate. And the way it'll work out is exactly what's shown in this bottom slide. It's effectively difference of the features.
Could you explain, so I think I sort of understand where the probability comes from, but could you explain how you'd use then logistic regression to solve for the beta? I'm a little confused.
Yeah. So the question is how I might use logistic regression to solve for this. So what's useful to say? So I'll describe something and then just tell me if it clarifies enough. It'll be simplistic, but I just mean this in trying to hopefully clarify what's going on. So I have this model, I collect data. My data set will look like samples of, in this case, Y can be, if I have K choices, Y can be which of the K choices I pick. Let's assume we're in the binary setting. So Y is just yes or no, did I pick option 1? I just always fix option 1, where option 1 could be one of 2 options or pick or not pick. Right? Either one is the same thing. So I have observations of yn, and I picked a featureization for my data set. If say I'm using this model, it is exactly equivalent to just sort of say x n is equal to zn1 minus zn2. And the way we know this is that we work through that only differences matter, or you can work through probabilities directly. And so now I have a data set yn, xn, 1 to big N, where the inputs are some set of vectors, of features for every example. The outputs are binary. Right? So yn is in 0 or 1. So I can go into more detail, but what I was trying to say is once I construct the data set, I can literally call model.fits. This is my data set. Get a data out, right? So that's what I meant to say. Okay. Is this clear? Or other questions about this? Yes.
Is there like a reason why sometimes we use extreme value noise as opposed to only use standard normal?
Yeah, so the question is, why do we use extreme value noise instead of standard normal? Extreme value noise is what gets you logistic regression. So I think I actually don't know in what order the real world thing happens. Someone here might know. But if I choose the model choices you're using logistic regression, then the ID noise that I need in order to make the whole math work is ID extreme value noise. Yeah, that's the answer to this question. Yes.
What does the noise actually end up looking like in like a rec engine or like some of these other like in voting? Or something?
It's a good question. So this is like, what is the empirical noise distribution that we see, and does it look anything like the choices made here? There's very little now. I'm not aware of, well, in ML, I've never seen the analysis, which is probably telling about how much we examine our models. I don't know the answer to that question. I think it's a good question. It's maybe easy to check. Go ahead.
Isn't it the case that we just don't care what it looks like? We just assume that it might look like this, and then it gives us this model, and we can work with it. Like, we don't really try to model the noise.
Yeah. So yes and no. So like the comments is, do we actually care what the actual noise distribution is? So pragmatically, the way, and actually, I'll go back to put on my ML hat, or even if you want to put your stats hat, but there are ways to check goodness of fits. Like, here's a literal data set. I can do train test splits. I can sort of check how well did my model work by fitting on a subset of data, checking how well it worked on a predictive set, and standard ML parlance. And it's to give you a sense of, am I making reasonable choices because I have a high accuracy in predicting on future data. So, from that point of view, if the error is high, then I have a bunch of interventions I could pick. I could decide that my featureization is incorrect, so I try to add a bit more features. I might decide my noise model is wrong, and if I'm careful, I'm actually examine the noise model and see if, somehow the noise is sort of in the wrong place. And so I might try to change the noise model so that it better fit my data. I might try a more sophisticated function class. So here's linear models. Might try a deep learning model, whatever. So all the standard things that you would do. So the thing I'm really trying to anchor, because again, this may look exotic, is that once you set up the problem and transform things appropriately, this looks literally like a standard machine learning problem. So the work is going from the choice model framing to setting up in a way that sort of this looks like predictive estimation. And all the standard tools that you would use from that setting would apply directly. So, that's the ML hat. If I wear a stats hat, I might do various kinds of tests of goodness of fit. I might do what else you might like to do. But all the standard tricks in different parts of the ecosystem for checking whether I fit a good model or not. We just use them directly here. So that was, I guess the question was initially, is the noise model right? And then a comment about, do we care or not? So, we care to the extent that we get a good fit at the end, and however we choose to measure fit. I work mostly in the machine learning world, so I would typically use like a train test split and look at out of sample performance as my measure of goodness of fit. Does that make sense to everyone, or any questions? Okay. All right. So you can make other choices. We've already talked about, or at least mentioned, that you could say choose a standard Gaussian noise model. Rest of it, again, we're just playing with the same objects, just playing with things. In this case, mostly function class, distribution, noise distribution, and range of items. So, a slightly different setup. I have a set of items. I allow for up to j alternatives, and I use the extreme value distribution. You could decide, again, this is somehow pragmatically the right choice, or you could say what I say, which is, this gets you to multi-class logistic regression. So either way, I think that's fine. And in the same way, you could replace extreme value noise with pro-bit noise. You get the Gaussian version of the same thing. I'm mentioning this because these are common modeling choices in lots of practical applications that people like to build. Okay, there's a question about correlations. So one option, if I'm interested in explicitly capturing correlations, one good choice might be, for instance, assume that the noise are sort of Gaussian with some covariance that describes how they're correlated with each other. And now my job is to both fit the parameters of the linear model and then the sort of correlations of the noise, and use this. The joints correlations, or the structure of the correlations, will change my fitting procedure a little bit, standard tools. Essentially, if I go to, I guess, our model fitting packages, or any of this, the packages are escaping me right now. I don't think scikit-learn has correlated noise, but you could use probably stats models, and Python would do it, or use R and sort of throw it in any of the standard packages. Questions? Or you could do it yourself. It's also fun. So less and less necessary, I think. Okay, so I've mentioned this a few times, but I just want to sort of ground this a bit more. So, we set up the problem, set up the choice model problem, said that there's a key assumption of an underlying true utility that fully describes the choices that people are making. And we've shown how we can convert that problem into a sort of effectively a multi-class problem, binary in the case where we're making this in binary, for binary choices. We've also explained a bit on degrees of freedom. So in particular, like this is the obvious one, differences, but also monotonic transformations. And the fact that you don't actually get a U, but you get something monotonically equivalent to U, because you can't actually fully estimate the monotonic transformation, at least using the standard approach. So you might try to use other tools to do this. We talked about logistic models. If I pick sort of extreme value kinds of noise, if I use Gaussian models, I get probit regression. All the examples we gave use linear models, but once I know how to set this up as a learning problem in this way, I can pick any model class I like. So I can throw in a deep learning model, decision tree. I don't know, what's your favorite SVM? I don't think we teach SVMs in our model classes anymore, but they're cool. What's your favorite model? I don't know. Whatever model you like, throw that in and fit it using sort of standard fitting semantics. So, you might use stochastic gradient descent as sort of the hammer we like to use for fitting many machine learning models, whatever optimization problem, optimization sort of machinery that you might use. In general, you would throw this in a existing toolbox. So scikit-learn, PyTorch, whatever, and sort of fits model. Again, hopefully this is clear. All of the standard decision choices that matter in trying to train good machine learning models matter in the same way for fitting choice models. So things like bias variance trade-offs, overfitting. So, generally you can pick more and more complex models. Generally, if you function your choice model here, the function class that you pick from mapping X to Y, the more complex it is, generally the more data you need. If you don't have enough data, generally you overfit, meaning, actually, just to double check, can someone give me a quick description of overfitting? Okay, sure. I mean, this hopefully is familiar from a class or two ago. Yes?
If you train your model on like just training data for long, or like training and test data, training data for long enough, it's possible that it's not going to perform very well on like real world test data.
That's correct. So yeah, you have good training performance, bad test performance, because the model is sort of picked up all the nuances of test data, but doesn't generalize to new data informally. But again, hopefully you've seen this before, even if you've forgotten it over the summer. Or some of you might be using this actually in practice. Okay, so all the standard stuff in terms of picking function classes, dealing with noise, modeling choices, all that stuff applies here. We talked a bit about this cross-individual thing. I think you might have asked the question. So very often you just do a pooling. In fact, almost all the ML applications of these that I know, most of the models don't disambiguate across individuals. Most of the choice models in psychology and economics do, because they think of that as an important signal. I think it's something that slowly the ML applications of the field of these toolboxes are slowly understanding might matter more and more. But if individual differences matter, then you might want to pick a model that has features not only about the items, but also like individual rating the particular item, or making the choice across particular items. Okay, you can make this more sophisticated. So far we've talked about binary choices, but you might, for instance, want sort of Likert scale style preferences. So now I'm choosing how much I prefer an item compared to alternatives. So, for instance, query, am I enjoying this class so far? And you might try to rank this 1 through 5. And so a standard model of something like this is, in addition to the utility, you have these thresholds for not just a binary choice, but now up to like k order choices simultaneously. So, in addition to fitting the parameters of the H function, you also need to find, it depends. In most implementations, you would fit both the A, B, C, D, and the H. It often actually works reasonably to pre-select A, B, C, D. So pre-select the thresholds and just fit the function that does the best job for those pre-selected thresholds. Again, this is set up as a standard, or can be set up as a standard maximum likelihood estimation problem. Use gradient descent, fit all the parameters. Okay. Okay, so we need to play with slides a little bit. I can use this, or implementing this, for instance, give you something like the ordered logic model. So linear model under the hood, thresholds for k options. I can work out from the utility and the threshold the probability of all the k options. So probably choosing 1, 2, 3, blah, blah. And given observations, I would fit this model. We'll try to fix the slides from here. Slight alternative version of this, generally called the Plaquette-Luce model, and ascribed to a model that came up in the 70s. Used a ton in biomedical literature for, say, ranking, often used for genetics applications. Sometimes used in econometrics. They like to call this the exploded logic model. Actually, don't exactly know why. I just know that this is the name. Is there anyone here who knows? If not, it might be fun to find out. I should find out maybe and have this in the next version. But very similar setup. But now I'm modeling the ranking over sort of J items. Again, posit a probability model. The way the Plaquette-Luce model works is that I have this sort of cumulative sum. So this is the probability of the first choice, given the first choice, probability of the second choice. So it goes from 2 to the end, given the second choice, probability of the third choice, all the way to the last choice that you're making. So it's probably a sort of the ranked set of J options. And again, all the other standard extensions, so you can do, these are linear models. I can throw some generic function class in there. I can expand on noise instead of using sort of extreme value style noise. I might use probit noise, correlated noise, all that stuff. Okay, so summarizing again what we've said a couple of times now. So again, the key setup in the problem is that you're measuring individual responses, sort of choice queries. You're observing people making decisions about preferences. The key assumption being made is that this decision-making is governed by a utility function. And then you make a choice about a model for that utility function. And once you have that, generally you'd have features that describe the items and perhaps the individual. And then you can set up the problem as a sort of machine learning problem, and then you fit the parameters of that model. This gives you a prediction or a model that you can use for prediction for future observations. And use standard maximum likelihood. You might add regularization, all the standard things that you would do for fitting models. Okay, any questions on modeling and any other setup? Yes.
The previous slide enforces counts, not ordering, right?
So this is useful in settings where the observations are ranked orders. So what I ask a person to do is rank item 1 through K, or 1 through J. I get to observe ranked orderings. I want a model for, so every time an individual comes in, they get J items and they get to order them. So the observations are these ordered lists. And I want a probability model for the ordered lists. And a simple probability model for the ordered list, what the pocket-loose model does is the distribution of the choice of this ordered list is the probability of picking the first thing on the list. Condition of picking the first thing was the probability of picking the second thing on the list. Then you're picking the second, third, fourth, all the way through J. And so this exactly looks like the probability of picking the first thing on the list, right? Which is a normalized sum of the score for the first thing normalized so that it's the probability. Condition on that first choice, I look at all the other choices, so 2 through J. And so this is a sum that starts at 2 instead of 1. And I keep doing this all the way to the end. Is that clear? Okay. Yeah. Good question. Thank you. Yes?
I'm wondering if we're trying to learn preference over, like, say, 3 options, and someone has circular preferences, what happens?
Yeah, so it's a great question. So the question is, this modeling assumption, we didn't state this explicitly. We will, I think. I hope, actually, I'm not sure. But the key assumption here, gone too far. The key assumption here is that the choices are such that they're effectively like linearly orderable, right? So this is one of the key axioms in using utility type. One way that people like to say it, particularly in economics, is that we're assuming that people are making rational choices, quote unquote rational. And the rational here exactly means that you don't end up with this transitivity mess, meaning like A over B, B over C, and then C over A. This setup will not allow that to happen outside of noise, but at least in terms of the expected behavior of the orderings. You assume in expectation that sort of all the options, the preferences are transitive, so you don't have this weird ordering issue that you brought up. In order to model that, you would need to change the underlying model. And that's one of the key, so actually really like that you asked this question because again, it's a key observation, a key assumption in using these kinds of models that can be broken. So what might you do if this is broken? So one option is sometimes this lack of transitivity can be explained by just not having rich enough features. So you might add more features so that it breaks things. you might, I guess, there are other classes of models, which we're not covering, but I should give references to, that allow for some intransitive preferences, which are similar enough and in a similar class. Generally, though, in most of these setups, assume that the sort of quote-unquote true preferences are quote-unquote rational. We're not doing this year, but last year we had sort of psychologists and marketing folks in the room. I had this fun conversation about, actually tied to this idea of noise, which is one of the ways that you might explain lack of transitivity. And there was this question of, when we see observations of preferences that break these assumptions, does this mean that humans are irrational? Or does this mean, so is it a problem? This is a bad way to say it, and this is not what I mean, but lack of a way of saying it. Are humans the problem because they're not matching our models? Or is it sort of our models or the context is not set up right? And I think a compelling answer to me is, I should look up the paper, and I think we might add it to our reading list. But a compelling answer to me is that when you see, okay, so one extreme is the rationality assumption is completely broken, and we shouldn't be using it. And we'll have at least one talk, I think in a week or so, that will talk about whether or not strong rationality assumptions are a good assumption for human choice, particularly in sort of complex settings like language models. So we'll engage with that question a little bit. Another setup is that sort of we're not modeling the problem the right way. This is a version of add more features or add more context. And sort of if we had sufficient appropriate contexts, we can almost always think of humans as rational. To my understanding, this is still a debate in, say, economics and other places that think about this problem much more carefully. I don't know a good answer to that. So, it's for here, I think we should think about it as a pragmatic modeling choice. We'll cover some instances where this is for sure broken and some tools for thinking about what to do when it's broken in a little bit. But it quickly becomes philosophical. I think interestingly philosophical, but often you'll observe data that sort of these kind of rationality assumptions don't hold. Thank you. Good question. Okay, so another important point that we haven't talked that much about is what does it mean to actually observe a preference? So there are at least two sort of broad families of preference observations. One is called revealed preference, meaning I observe people making real choices in sort of real situations. So for instance, I observe people actually come to my car site and picking the car that they want to choose. Often this is offline, but this captures sort of real behavior of people in real contexts. So that's sort of one version of it. Another version is you put people in a room. You say, imagine you were going to buy a car. Here are some options for cars. Which car do you think you would pick? So these are often called stated preferences. The key difference here is that this is generally for the human, this is hypothetical, right? So they're not making a, say, economic choice. They're not actually putting money to buy an item. They're instead trying to think through their mental model of how would I make a choice if I was faced with this choice in a real setting. So the big plus of the stated preference is that you can control a bunch of the context. So you can do well-controlled experiments. You can balance and sort of control for confounds and things like that. But the big issue that's often brought up with stated preference is that it may be unrealistic. People might state that it might choose something. This often comes up in, say, election choices. That people state they will pick a certain option, but it will actually make a different choice when they really need to make the choice in the real world. So this is a meaningful issue. I think it's one of those things that's not engaged sufficiently in our field, for instance. So for instance, in language models, I guess there's a bit of a weird gap because we don't have good grounding to, say, downstream impact decisions to make a big distinction between revealed and stated. But I'd argue, and often in, say, language model experiments, we're thinking about this through the lens of stated preferences. Someone's in a room, I give them a bunch of language completion. I ask them, which would you prefer? There's no cost to making a decision in either way. It's sort of your mental model of what you think might be reasonable. So again, this is a sort of meaningful gap. It's, again, something that's considered semi-controversial depending on the setting that you're in. Again, the big issue with stated preference is that you wonder if people are actually going to sort of tell you the real thing that they would do if they're sort of simulating their decision process. However, in real preference, you have issues of confounds, you have issues of coverage. So, the set of choices that people make may not cover all available choices sufficiently such that you can estimate good parameters for how people are thinking about sort of all the different choice options that they might be making. Is this clear? This is actually quite an important idea, so I want to make sure that it's clear-ish. Okay, cool. Any questions on discussion so far?
Oh, I'm just curious for your perspective, actually. So, I mean, obviously this is an important distinction, but like, you seem to also emphasize like the modeling choice preference, right? Like, logistic, whatever, model you want to use. And do all three interact in your mind at all? I mean, the experimenter chooses, right?
Indeed,
like,
indeed.
They want stated or all these things as well.
Yeah. So yes and no. So the question is, does, say, the experimenter choice of stated versus revealed interact with the underlying model class that you might use, for instance? So practically, the choices seem orthogonal. Sorry, no. Conceptually, the choices seem orthogonal. Practically, they interact in the following way. So again, with revealed preference, you have a bit less control over the sample space. What this means is that you can end up in estimation gaps where sort of some choices are way undersampled in some parts of, say, X space, way undersampled so that your model is bad. And so a pragmatic choice in that setting is to pick a model that's, say, more restricted so that it does a better job given restricted choices in terms of options. If you're doing controlled experiment stuff as well, so you think about this as like controlled two-sample testing kind of thing between options, then the observation model might also impact how you think about what a good preference model might be. So they do interact, but I think it's a little bit weirdly nuanced, though important. I don't know if I actually... It's a good question, actually. It's not one I've thought about as directly, but it's an important design choice here. You have thoughts on this? Or...
No, I mean, it's actually the first time I was putting that together. That,
okay.
Like, you actually have to choose maybe different models.
Indeed.
That are most appropriate for the kind of preference. Yeah.
Maybe you and you.
Yeah, don't they actually interact? Because, say, I said on YouTube, I don't want to see this, but then I kept clicking on it anyway, and the model has to choose, like, who is right? Like, is it your choice of, like, your revealed preference, or is it your stated preference?
When you say interact, so I think the earlier question was about the learning model that you choose for the observed data versus the observation process, and sort of whether it's, if you like, I don't know, well, what kind of observation process between the two options? Could you, I guess...
Or so I'm saying that, are they really separate models, or actually, they actually should be in the same model?
Oh, okay, yeah, so I said this badly. So, what I meant to say, and thank you for bringing this up, it wasn't clear. I guess conceptually, they seem like independent decisions. Practically, they interact because, like I said, if I'm in a real preference setting, this often will lead, in many interesting real preference settings, this leads to like a specific distribution skew in the data I get to see. Right? So generally, in stated preference, I can design my experiment so that everyone has to pick over every possible option, so that sort of things. Essentially, the observations of Y and X have a good coverage over all the possible options, such that maybe it's easier to fit a more complicated model or something like that. Whereas if I'm in a real preference setting, I don't have control over the sampling process. I'm just seeing what the world is giving me. And so, generally when you don't have control over the sampling process, it's pragmatic to use simpler models. It's a reasonable decision to make. And in many settings, it will tend to work better because, or you could do that, or you could do more sophisticated things to control for distribution shift, for instance. The fact that you get the skewed distribution of what you'd like to see, which is some coverage of all the different preferences. So my answer is they interact with each other and interaction matters, but I think of it as a bit subtle, or maybe it's not subtle. I think of it as subtle, though. Yes.
Yeah, I was just thinking, back to the YouTube example, like which one would I think would be more reliable if I had a labeled data set with a bunch of people and saying which videos they preferred given, some information about them. The example that I always think about is like my 3-year-old daughter gets my phone and it starts going crazy and starts swiping, clicking, and stuff like that, and that happens. And sometimes
it's almost a noise, right?
Phone, so if you use the implied, did I complete the video, which is like, a very good signal, but it just requires some cleaning, and then it can actually miss you if you just use it raw.
Yes. Again, I think about this as like, the real world is messy and noisy, and you have to make pragmatic choices. I mean, the counter argument is if I'm requiring stated preference, I guess it's very well known that people telling you what they think they would choose and what they actually choose are not the same. Right? That's the actual gap, right? So the trade-off that you're making is, are you in a situation where either you don't care, or you just really want to be able to control the experimental setup, or do you really care about sort of really seeing what people's choices are? I like the election one, actually. Like, who would you vote for? Ask in this room. I think people may pick options that think, we're in the West Coast in California, what everyone might agree. You might have a different actual preference that you may not want to state because you don't feel comfortable stating it in a room like this. So here's for sure a gap, right? There's a stated preference, which is this: I'm going to imagine. And in addition to imagining a choice you'd make, you're also maybe taking into account who's asking you the question, the context, your opinion, how you think they might think about you making that choice. All that stuff gets folded in. In real preference, you're looking at the actual choice people make, often when there's some consequence on the line. There's an economic or buying decision. There's some real-world outcome that's tied to it. So it's a meaningful gap. I may or may not have done a good job, like really clarifying that these can actually be like night and day different from each other. Like sort of your reasoning and trying to imagine a preference versus actually making a decision in the real world. And so the data, in the same exact situation, but collected in two different settings, in general, will not agree, actually.
Is there anyone that uses both and uses a dummy variable? That bias kind of.
So some of this is modelable. I haven't seen that much work trying to engage with this, though I'll be surprised if there isn't, given how big this area is. If also you don't mind, I want to make sure we're close to time. So I love the discussion, but I may push the rest of this offline so we can finish discussion today. So we'll skip the exercises because we had a good conversation and didn't get to this. I think I'll push the ideal point model to next week. So actually, we can end here. So let's actually just go with maybe the last question.
I was just going to say that I think a clear point where you would want to teach out is like people, like for example, if people's own money is on the line, they tend to be risk averse. And then you want to use your quantitative Tversky preference models. And then if you have people for stated preferences in simulation, then maybe they're like an expected utility maximizers instead because it's not their own money on the line. And so that's to me seems like a clear case where there are two different preference models, so it makes sense depending on the.
Yeah, I think those are part of it. I think there's additional nuance that makes, I guess, not as clear a separation of use this in pointed situations. Yeah, maybe we'll just end that there for now, but it's a good point. If you don't mind, I think we're at time, so we'll just take the rest of the questions offline. But good discussion today. Thanks, everyone.